thank you very much, everyone, for joining us in the room and online today. Before I begin, I would like to first acknowledge the traditional owners of the land on which we meet today and pay my respects to their elders, past, present and emerging. And I would like to extend that respect to any First Nations people participating in our seminar today. So it is my very great pleasure to introduce today Miriam Hamladar. So Miriam she's our speaker for today. She received her training as a chemical engineer at Arak University in Iran and then completed a master's at the University of Tehran in energy systems engineering. And she's been waiting patiently for 2 years to come to Australia. But because of our international restrictions with COVID and stuff, she's had to wait a while. But she was finally arrived in Australia in July last year. So it's absolutely wonderful that she's arrived and has actually started her PhD. So Miriam is undertaking a PhD at the University of Melbourne with one of the largest geothermal research groups in Australia. Miriam graciously accepted an invitation from GA to undertake an Australian postgraduate research internship and to make a slight detour with her PhD. So I had a particular interest in how could geothermal in Australia contribute to hydrogen production? And so Miriam has very kindly taken out 5 months of her PhD to just make a slight detour and do an investigation of that. So we're going to find out all about her findings today. So that's enough from me, and I would like to hand over to Miriam to share what she's found. Thank you very much, Miriam.
Hi everyone, I'm Miriam and thank you for being here. Today I'm gonna talk about hydrogen production from geothermal energy. I've done this research as an internship from the Geoscience of Australia, and this research is supervised by Dr. Andrew Pites from the Geoscience of Australia and also Professor Guillermo Narcilio and Dr. Graham Bresmo from the University of Melbourne. I'll start my presentation with a brief introduction about the hydrogen production and its importance. Then clean hydrogen strategy in Australia. After that, geothermal drive and hydrogen production routes will be explained. Then geothermal resources in Australia will be reviewed in order to find the potential geothermal routes for producing hydrogen in Australia. After that, integration of geothermal with solar energy will be explained. And finally, I will conclude my presentation with identified research challenges and research gaps for future work. Let's start with this main question: why hydrogen is important. Hydrogen as a carrier, as an energy carrier, has the capability of energy storage at both larger scale, mainly for renewable energy integration, and at a smaller scale for transportation. Generally, hydrogen can be used in different applications that, based on the final user, can be classified as industry for producing chemical feedstock and also as an energy source in transportation for different vehicles, ships, aircrafts, power generation in fuel cell technologies, and finally heating and cooling of the building. Another important perspective on producing hydrogen, especially clean hydrogen, is related to its potential contribution in climate change mitigation and also CO2 emission reduction. Given all of these benefits, some countries all over the world have horizons of movements toward hydrogen economy, where hydrogen can be produced, stored, and even exported as a main carrier energy. In spite of the growing role of renewable energies in the energy sector, these resources have some challenges and issues, such as intermittent nature and storage difficulty cause imbalance between demand and supply of energy. While with integration of hydrogen production technologies with different kind of renewable energy resources, hydrogen can be produced and stored to use once it's required. So hydrogen production technologies can be considered as the appropriate option to manage imbalance between demand and supply. As a result, renewable and hydrogen-based energy systems would have an important role in the future energy supply with positive effect on energy security, environment, economy, final users, and finally sustainable development. So it's important to give a lot of attention on researching and developing hydrogen production technologies as a main and important steps toward improving a successful hydrogen economy. Hydrogen can be produced through different routes based fossil fuel and renewable technologies. Hydrogen extracted from fossil fuel feedstock is known as a gray hydrogen, releasing huge amount of CO2 emission into the atmosphere, or as a blue hydrogen by integration with carbon capture storage, it avoids CO2 emission into the atmosphere. On the other hand, clean and green hydrogen can be produced from non-fossil fuel feedstocks such as biomass or water. Splitting water through thermolysis and electrolysis process are the most widely used of extracting hydrogen from water. Currently, more than about 95% of global hydrogen is producing by fossil fuel routes, and only less than 5% of global hydrogen is producing by renewable routes. Since producing hydrogen from fossil fuel technologies are more affordable than renewable ones, while renewable ones are more sustainable as a result of having a lower carbon footprint. So there is always a trade-off between affordability and sustainability of producing hydrogen through different routes. Water splitting through electrolysis process is a mature technology that can produce hydrogen with high purity from water. This process can be run with electricity as an input to activate water decomposition into hydrogen and oxygen. Electrolysis process based on the different technologies can be classified as alkaline, proton exchange membranes, solid oxide electrolyzers. Two former technologies are known as a conventional electrolysis with a low operating temperature up to 80-90 degrees centigrade and also low efficiency, so they need high electricity as an input for decomposition of water process. The later technology is known as an unconventional electrolysis with high operating temperature in the range of 700 to 900 degrees centigrade, and also with high efficiency, which leads to a lower electricity consumption for extraction of hydrogen from water. Alkaline technologies have lower capital cost than PEM technologies, while PEM technologies have more technical benefits such as rapid response, which is more important when it's integrated with renewable energies. Let's talk about the importance of producing hydrogen in Australia. In line with a technology investment roadmap in Australia, clean hydrogen strategy as a low emission technology can support Australians' low emission plan, as well as development of both export and domestic hydrogen industry, so that make Australia a global leader for producing and exporting hydrogen by 2030 and 2050. Based on the national hydrogen strategy, clean hydrogen in Australia can be produced through renewable electrolysis process, as well as fossil fuel route integrated with carbon capture storage. However, in a successful hydrogen economy, the cost of producing clean hydrogen must be competitive within the market in comparison with fossil fuel routes. For this reason, it's projected clean hydrogen will be cost competitive within the market in Australia when the cost of that is $2 per kilogram or less. As a result, Australia is planning to meet this economic stretch goal, producing hydrogen less than $2 per kilogram by 2050. Here the question is that how a clean hydrogen through renewable electrolysis can be cost competitive. This figure shows the production cost of hydrogen from renewable electrolysis, and as it's obvious, the cost of electricity and also the capital cost of electrolyzer technologies have great contributions to the production cost of hydrogen. So decreasing the cost of electricity and also electrolyzer technology would be critical in meeting economic stretch goal of producing hydrogen in Australia through development of low cost and high efficiency electrolyzers, and also using cost effective renewable electricity to run water decomposition in the electrolysis process. In terms of electrolyzer technology, it's projected that alkaline technologies have less cost for producing hydrogen in comparison to the PEM technologies as a result of their lower capital cost. In addition, high temperature electrolyzers can be beneficial economically to produce clean hydrogen as a result of their lower electricity consumption. In terms of electricity cost, geothermal energy has lower operating cost in comparison to other renewable energies such as solar and wind due to their high capacity factor. Another important point here is that based on the literature, hydrogen production by using geothermal energy can be more affordable than other renewable energies. So it's important to investigate different routes of producing hydrogen by geothermal energy. Hydrogen can be produced by geothermal energy through different routes. Direct use of geothermal steam can be applicable for producing hydrogen in tectonic spreading zone and volcanic regions where huge emission of hydrogen with other components such as methane, CO2 and CHR can be released into the atmosphere. But producing hydrogen through geothermal steam needs gas cleaning technologies. Geothermal heat in thermochemical process can be used to produce hydrogen from water decomposition by using different thermochemical cycles. This process is run based on the heat at high temperature of about 800 to 900 degrees centigrade. However, there are some low temperature cycles that may give an opportunity for producing hydrogen via geothermal heat. This figures shows the possibility of geothermal energy in thermally hydrogen production via cycle operating in temperature of 300 to 500 degrees centigrade. Another route is using geothermal electricity for producing hydrogen from water splitting in conventional electrolyzers such as PEM and alkaline technologies. And finally, using both geothermal heat and electricity can be used to produce hydrogen from water splitting through unconventional electrolyzers or thermochemical hybrid process. Thermal decomposition of water for producing hydrogen by using a low temperature or hybrid thermochemical cycle still needs research and developments in terms of efficiency movement and also cost reduction. Unconventional electrolyzers for producing hydrogen are more efficient in comparison to the conventional low temperature electrolyzers as a result of their higher operating temperature. So they need lower required work to run a water decomposition process, so they can have lower hydrogen production cost. The correlation of temperature and also the required energy for water splitting through unconventional electrolyzer can be seen from this figure, right-hand side figure. Based on this figure, required energy for water splitting can be classified, can be divided as electrical energy and also thermal energy. So since electricity consumption serves as a main contributor to the energy consumption of water splitting, increasing the temperature of water entering to the electrolyzer can improve the efficiency as well as decrease the required energy, so that have positive effect on the cost of producing hydrogen. Let's learn a bit about this technology. Some of the required energy for splitting water through high temperature electrolyzers can be supplied by geothermal energy to vaporize water up to maximum temperature of geothermal reservoirs. Then resulted steam can be overheated in some heat exchangers, recapturing heat from the outlet of electrolyzer. And finally, by applying electricity, thermochemical reaction of water decomposition can be run. The cost of hydrogen production through high temperature electrolyzer is driving still with electricity cost and also capital cost of the electrolyzer, but the contribution of electricity cost in this process decreased as a result of using thermal energy to improve the temperature of water entering to the electrolyzer. Now that we consider different routes of producing hydrogen by geothermal energy, we should investigate the different geothermal reservoirs. If we want to classify geothermal reservoirs in a really general way, we will have two overall groups as the hydrothermal reservoirs and also hot dry rock reservoirs. Most of the exploited reservoirs all over the world are hydrothermal reservoirs with volcanic rocks. That high temperature can be found at the shallow depths, less than 3 kilometers. Another type of hydrothermal reservoirs are hot sedimentary aquifer with sedimentary and fractured aquifers. These reservoirs can be found at a location without volcanic and tectonic activities, such as Australia. These reservoirs have high natural porosity and permeability, so water circulation occurs naturally. In hot dry rock reservoirs, which are known as the enhanced geothermal reservoirs, higher temperature, about more than 200 degrees centigrade, can be found at deeper depths, about more than 3 kilometers. These reservoirs are on fractured rock with low porosity and permeability, so the water circulation within these reservoirs occurs artificially with some existing technologies. In Australia, due to the lack of volcanic activities, hydrothermal reservoirs are as a shallow and deep aquifers. Shallow aquifers can be used just for direct use application of geothermal energy as a result of having lower temperature, less than 100 degrees centigrade at shallower depths. But deeper aquifer with a higher temperature in the range of 100 to 180 degrees centigrade can be used for electricity generation from binary power plant cycles, in addition to direct use of geothermal energy. Australia also has a lot of hot dry rock reservoirs where temperature more than 200 degrees centigrade can be found at the depths of about 5 kilometers. These reservoirs may be useful, may be suitable for electricity generation as a result of having high temperature, but according to some exploration activities, power generation from these reservoirs wasn't successful economically. However, in Australia, there have few small-scale successful projects for power generation from hot sedimentary aquifer that shows the possibility of Australia for producing power geothermally. The first successful geothermal project was a 20 kilowatt ORC in Muka, operated for 3 years by using about 86 degrees centigrade water from an existing water bore at a depth of 1.5 kilometers. The second project was related to an 80 kilowatt ORC in Bridgeville, operated for more than 20 years. By using 98 degrees centigrade water from a town water bore at the depth of 1 kilometer. And finally, and last geothermal project is related to a 310 kilowatt ORC in Winton, commissioned in 2019 by using water at a temperature of about 86 degrees centigrade from an existing water bore at a depth of 1 kilometers. So the successful projects of power generation from hot sedimentary aquifer and also identify productive aquifers in some sedimentary basins in Australia from one hand, and unsuccessful project from enhanced geothermal reservoirs or hot dry reservoirs. From the other hand, confirmed the possible geothermal resource in Australia for producing power geothermally or hot sedimentary aquifer with the temperature of less than 100 degrees centigrade. Since organic ranking binary cycle or ORC is applicable when the source temperature is about 90 degrees centigrade, so this kind of power plant is suitable for power generation in Australian applications. However, the efficiency of converting heat to the electricity in this kind of power plants, ORC power plant, is low at the temperatures below of 150 degrees centigrade. As a result, it's important to improve the efficiency of ORC for producing power in the Australian context based on the different methods. There are different configurations of ORC for producing power. Among them, some more advanced configurations such as dual pressure cycle or recapitulated, regenerated cycle with have additional equipments can have improved efficiency than simple ORC power plant. Another advanced configuration of ORC is integrating the power plant with thermoelectric generator. Thermoelectric generator can replace with the condenser of ORC in order to turn waste heat of the power plant into the electricity directly and then improve the efficiency and the power of the system. Another way to improve the efficiency and also power and finally hydrogen rates by using geothermal energy is integration of geothermal energy in Australia with other renewable energies such as solar energy. Solar can be used to preheat geothermal fluid directly through improving the temperature of geothermal fluid before entering to the ORC. Solar energy also can be used to superheat the working fluid of ORC by improving the temperature of that after the first heat exchanger. In addition to the low efficiency of ORC power plant powered by geothermal energy, especially in the Australian context, geothermal reservoirs have another barrier, including the high initial cost that can limit its application for producing power and finally hydrogen production. For this reason, extraction geothermal energy from existing oil and gas well in oil fields can be important. Geothermal energy can be extracted from existing oil and gas well in oil field through two routes. Produced water from active wells as a byproduct can be used for geothermal applications based on the temperature it has And also injected working fluid to the target depths of abundant well can be used as another route to produce geothermal energy from existing well in oil field. In this manner, working fluid is injected and circulated in a closed loop of a double pipe or U-tube heat exchanger as a well bore in order to extract geothermal energy. In active wells, the power production relies on the rate and also the temperature of produced water and also the operation of the oil and gas well. While the power generation can be more manageable in abundant well as a result of more control in the temperature and the rate and also the type of the fluid which is injected into the wellbore, and also it relies on the circulation of fluid in the wellbore, not the operation of the well. However, the geothermal reservoirs in oil fields have low to moderate temperature, so it can cause lower efficiency of ORC, and also it can limit the application of some oil and gas wells in oil field. One possible way to overcome this challenge is a downhole power generation in oil field. So integrating thermoelectric generator with heat exchangers in the abundant well. In this manner, thermoelectric devices are installed on tubing a pipe as a producing pipe, and also as a result of temperature difference between tubing and also injecting pipe, thermoelectric devices can produce power from the heat directly. The right-hand side figure shows the vertical abundant well integrated with thermoelectric generator, and the left-hand side figure shows the horizontal configuration. Downhole power generation in oil field can facilitate more oil wells for power generation, since thermoelectric devices can operate in a variety of temperature as low as 30 degrees centigrade. Downhole power generation also can eliminate the need for transportation of produced water to the surface that can cause heat loss a lot. And also this technology, downhole power generation, can be integrated with conventional ORC binary plants to increase the rate of power generation and also rate of hydrogen production. Until now, we considered some improvements on the ORC power plant driven by geothermal energies in Australian context. So let's take a look at the whole system for producing hydrogen by using geothermal energy. Based on the thermodynamic and thermoeconomic assessments for producing hydrogen through geothermal energy, there are different important parameters having important effect on the efficiency of the whole system producing hydrogen, and also the rate and the cost of produced hydrogen. In this manner, improving the efficiency of power plant, decreasing the heat loss in different components of the power plant, finding and using optimum working condition in terms of geothermal field and also ORC components, and water preheating before entering the electrolyzer process can have great effect on the cost and also the rate of produced hydrogen that should be considered during the development of hydrogen production system. As a summary and key works, we can say geothermal reservoirs in Australia have low temperature up to 100 degrees centigrade. So ORC power plant can be a likely option for power generation in the Australian context, but this configuration may not be efficient enough to be viable economically. So using more advanced technology and also decreasing the heat losses from the cycle by applying thermoelectric generator devices can improve the efficiency and the flow rate of power, the rate of the power and hydrogen as well. Integration with solar energy is another possible way to improve the temperature of geothermal and also improve the temperature of the working fluid to improve the efficiency of the system. Extracting geothermal from oil field is another possible option, but potential of having a suitable flow rate and temperature need to be considered. So far, we studied the potential routes for producing hydrogen through geothermal energy. However, there is a lot to be done. And now I've identified some research challenges and research questions for future work. So there are multiple key elements that are so important. The first element is geothermal energy resource, hot sedimentary aquifer in Australia context. Using more update and accurate data related to lithological properties of geothermal reservoirs, hot sedimentary aquifer in Australia, must be considered in order to investigate the feasibility and appropriate the property of hot sedimentary aquifers for producing power and also producing hydrogen. So here the role of the Geoscience of Australia would be highlighted because this organ can provide us more accurate and up-to-date data for have a better investigation of the potential of hot sedimentary aquifers. And also geothermal wells can play an important role in hydrogen production system in terms of energy conversion and also the cost of producing hydrogen. So it's important to develop a numerical model of geothermal well as the main and important steps in development of hydrogen production systems in order to investigate the feasibility and thermal capacity of the wells for producing power and finally hydrogen rate. Since geothermal gradient changed by the location, temperature of geothermal drilling depths and drilling costs are important factors that must be considered during the development of the hydrogen production system by geothermal energy. And since the quality of extracted energy from the well can be increased by drilling deeper depths, but at the other, from the other hand, the cost of drilling will be increased. So there is affordability between the quality of energy extracted and also the cost of the drilling depths. So it is important to find out optimum drilling depths. In terms of water resources, water availability, accessibility, and the price and purity of water are another important factors that must be considered in order to find out most feasible hot sedimentary aquifer for producing power and hydrogen. And since geothermal energy can be used to run a desalination process for producing fresh water for the electrolysis process, it is important to investigate the possibility of integration of hot sedimentary aquifer with the desalination process in order to create a multi-generation system and produce at the same time power, hydrogen, and fresh water. In terms of potential of oil field, proper flow rate and temperature of produced water from an active well must be considered to investigate the most feasible wells for producing geothermal energy and using this power in producing hydrogen. Temperature, flow rate, and the type of the fluid injected into the abandoned well, and also installation type of pipe during within the well bores, and also bottom hole temperature of the abandoned well are important factors must be considered during development of accurate numerical model of oil wells in order to investigate the potential and the possibility of abundant wealth for producing geothermal energy and using that power geothermally for hydrogen production. Power plant elements among different configuration of ORC power plant, advanced configuration and those with decreasing heat loss by using thermoelectric generators can improve the efficiency of power plant and also the efficiency of the whole system producing hydrogen. But at the same time, this configuration can burden extra cost in the system producing hydrogen. So it's important to find out the efficient and cost-effective configuration of ORC power plant in the system producing hydrogen. The cost of equipment, geothermal extraction, the cost caused by heat losses during electrolysis technology, and also ORC components are important factors that must be considered during economic assessment. Using and finding optimum operating conditions have important effect on the cost and also the rate of produced hydrogen. So all of these factors must be considered during development of the system that produce hydrogen, and using optimum operating condition can have a positive effect on the performance of the system. Integration with other renewable energy is another important element. Considering the temperature and the temperature of geothermal and solar inputs, such as solar irradiance, so it's important to investigate the capacity factor map of solar energy in order to find the most feasible and ideal location for integrating of hot sedimentary aquifer with solar energies. And here the role of Geoscience of Australia can be highlighted again in order to help us, because Geoscience of Australia have such accurate capacity factor maps for solar and also other renewable energy, such as the wind, that can be help us in order to find most feasible and appropriate location for integrating hot sedimentary aquifer with solar energy. Given different type and also the size of the solar energy, it's important to find out efficient and cost-effective design of the solar energy. For example, different kind of solar collectors in the system which is integrated with renewable energies. And since thermal energy system can improve the productivity of solar and finally produced hydrogen, and given a different type of size and type and size of the thermal energy storage technologies, it is important to find out optimum size of thermal energy storage. In terms of thermolysis elements, in conventional water splitting through conventional electrolysis, the efficiency, the type, the operating temperature of the electrolyzer technology, and also the temperature of water entering to the electrolyzers are important factors that must be considered during development of a system producing hydrogen. And since geothermal energy as a thermal energy source can be used to preheat water during the process of hydrogen production, it's important to investigate the possibility of hot sedimentary aquifer in Australia for preheating water before entering to the electrolyzers. In unconventional electrolyzer, the cost of thermal energy, heat exchangers, and also cost of electricity, especially using low-cost electricity such as ultra solar technology that is introduced as a new technology in roadmap of Australia, must be considered during the techno-economic optimizations in order to find out the feasibility and the possibility of unconventional technologies for producing hydrogen. And conducting thermodynamic and thermoeconomic analysis are is so important for using low temperature and also hybrid thermochemical cycles for producing hydrogen. And also ecosystem consideration is another important element must be considered for hydrogen production systems via geothermal energy in Australia. Geothermal wastewater can be injected or discarded. So by considering different risks and benefits, such as financial consideration, location of injection well, and temperature of injection as the risk, and also prolonging lifetime of the reservoirs, minimizing the environmental impact as the benefits of injecting wastewater, geothermal wastewater into the injection wall must be considered. And it's important to conduct an environmental assessment during the lifetime of the system, including drilling stage, construction stage, maintenance stage. And the effect of such system for producing hydrogen by geothermal energy in Australia must be considered on the human society and ecosystem through multi-objective optimization method. Thank you so much for your attention and patience, and I would be happy to answer your questions.